Hello everyone and welcome back to Diksha Karnataka YouTube channel, and you are watching KCET 60 out of 60 in physics series, where we are currently discussing ray optics and optical instrument. We have already completed ray optics and optical instrument part 1, where we have talked about reflections. Now today we will start with refraction, and tomorrow there will be a very important day for you. In the morning you will receive your KPL question paper 5, and you can download it absolutely free by joining our WhatsApp group. If you join our WhatsApp group tomorrow morning, you will receive question papers for physics and chemistry as well, I guess, and you have to download the question paper, solve it on your own, and then at night I will be back with the solution of all those questions. So what are you waiting for? Please join our WhatsApp group. Link is given in the description, and click on the notification so that you get the notification whenever we are posting one video in that. So don't wait for tomorrow, do it now, right? And let's start with the list of content for today's topic. So what we are all going to discuss? We are going to discuss law of refraction, then we will discuss about refractive index, then total internal reflection, very important concept, and then application of TIR. We will look into few applications of TIR and how this can be beneficial for you for your KCET 2025 exam. So now let's start with laws of refraction. Okay, this is now let's look into laws of refraction. So first we will start with laws of refraction. Okay, what is the laws of refraction? The first law of refraction is similar to that of second law of reflection, that is the incident ray, the refracted ray, and the normal to the interface at the point of incidence all will lie at the same plane. So basically let us first briefly understand what is refraction. So refraction is when in a ray of light falling between the line separating the two media. Okay, that is, there is one media, that is, suppose this is air and this is water. Okay, light is trying to travel from air to water. So what will happen in this case? Some part of the light will be reflected back and some part of the light will enter to the second medium. Okay, the part of light that entered in the second medium, that light is called refracted ray. So this is a refracted ray, right? Now this incident ray and reflected ray are on the same plane. We have already learned that. Not only that, this incident ray, this normal, and this refracted ray, they are also on the same plane. So basically you can say that incident ray, reflected ray, normal and refracted ray all lie on the same plane. So basically they are member of a same family, right? So they are a member of same family. So you can understand that they are all lying on the same plane. Basically they are staying in the same home, same building, right? Now the second law is very important, that is Snell's law. Okay, what is Snell's law? The ratio of sine of the angle of incidence. Okay, the ratio of sine of the angle of incidence to the sine of the angle of refraction is constant. So basically what is the meaning of that? We know that we always measure the angle of incidence with respect to normal. So this is the angle of incidence, and we always measure the angle of refraction also with respect to normal. So this is the angle of refraction. Unlike in reflection, where incident ray was actually equal to that of reflected ray, here the ratio of sine is constant. Okay, so ratio of the sine is constant. Now if the incident angle is given by I and the refraction angle is given by R, then from this law we can write that sine I divided by sine R equals to constant, and that constant is represented by n21. Now what is n21? We will come to that in a short while, but the most important part is this is a constant for a given pair of media. Okay, media is the plural of medium. Medium means one, media means more than one, right? So for a given pair of media, this is a constant value, and that constant is called refractive index. Okay, so that constant is called refractive index. Okay, and refractive, not only the refractive index, it is called the refractive index of the second medium with respect to the first medium. Okay, so refractive index of the second medium with respect to the first medium. Now there is a law that is called reversibility of light ray. So law of reversibility, what is the meaning of that and why I am saying that? Let us understand that. Suppose a ray of light is traveling from this medium to this medium, this is the angle of incidence, and after entering the second media, now this is the angle of refraction. Okay, from this we can write this is the first medium, this is the second medium. So refractive index of the second medium with respect to the first medium will be sin I by sin R. You should be careful. This is the refractive index of the second medium with respect to the first medium. Now we will learn about something more, absolute refractive index, etc. But what will happen if I reverse the path of the ray? What will happen if I reverse the path of the ray? That is, I reverse the path of the ray and I sent a light along the same path, okay, but in the opposite direction. Now I am sending a ray from medium 2 to medium 1, okay, such that the incident angle is now R, and then from the reversibility of light, this angle should also be I. Okay, so the refracted angle will now be I. So from that we can write that n12, that is refractive index of the first medium with respect to the second medium, is now incident angle is what? Incident angle is R and refracted angle is I, right? These are just names, so we can write it like that. Now what is sin R by sin I? Sin R by sin I is basically opposite of n21. So what I am trying to say that if refractive index of the second medium with respect to first medium is suppose 5, then refractive index of the first medium with respect to second medium will be 1 by 5. Okay, now this is also called relative refractive index. We will come to that in a while, but you should remember that refractive index of the both medium can be calculated using this formula. So even though it is only talking about refractive index of the second medium, if second medium is given with, if you just inverse it, that is 1 by that value, then you can get the refractive index of the first medium. Okay, now if n2 is greater than n1, so in this case if n21 is greater than 1, n21 I am using this color. So suppose n21 is greater than 1, that means sin I should be greater than sin R, right? So I is basically greater than R, or R is less than I, right? Simple as that. So what will happen in this case? In this case, the ray of light which is coming from this, suppose the incident angle is 45 degrees, so R will be less than 45 degrees, suppose this is 30 degrees. Okay, so that means that the second medium, the light ray is bending towards the normal. Okay, so the light ray which was coming like this, after entering the second medium, it bends towards the normal. Now this happens when light is entering from optically rarer medium to optically denser medium. Okay, this term optically denser is very useful, very meaningful. It is nothing to do with mass density, it is optical density. Optical density means if the ray is traveling to a medium, if it bends towards the normal, that means the medium is optically denser. Okay, so this is called medium 2 is called optically denser compared to medium 1, and medium 1 is called optically rarer compared to medium 2, right? Now on the other hand, if n21 is less than 1, Okay, that is opposite case is happening. Now light is suppose traveling from this to this, so you can follow the white arrows now. You can follow the white arrows now. Okay, so light is traveling from this medium to this medium. Okay, so in that case what happens is the angle of incidence is less than that of angle of refraction, that is angle of refraction is more than that of angle of incidence. Okay, so what this is called, when the incident ray is denser medium refracts into a rarer medium. So from denser medium now light ray is traveling to a rarer medium. So denser and rarer is very important concept. So if they ask you light ray is traveling from one medium to another medium and it bends towards the normal, then what type of medium it is? It is a denser medium, optically denser medium. Okay, now optical density should not be confused with mass density. Mass density is mass per unit volume. We already know that mass density generally represented by rho is equal to m by v. Okay, mass density is m by v, but optical density should not be confused with it, even though in most cases higher mass density represents higher optical density, but there are very good number of exceptions to that, so you cannot confuse with mass density and optical density. So for example, it is possible that mass density of an optically denser medium may be less than that of an optically rarer medium. So optical density is the ratio of speed of light. We'll come to that as well. For example, turpentine and water. Okay, turpentine is basically lighter than that of water. So if you pour turpentine on top of water, turpentine will float in water. Okay, because its mass density is less than that of water. Right, so mass density less means it will float. For example, wooden piece will float on water because its mass density is less than that of water, but an iron nail will sink because iron nail has higher density than of water, right? Similarly, but in case of optical density, the optical density of turpentine is greater than that of water. So turpentine has higher refractive index compared to that of water. Okay, so if the refractive index of a medium with respect to air is higher than a refractive index of the another medium with respect to air, then that higher refractive index medium is called optically denser medium. So similar to mass density, you can consider refractive index is a medium of optical density. So you can consider this as an optical density. Now one more thing, this term refractive index is a unitless quantity, right? It's a ratio of angle of sines. Now angle itself is a unitless quantity or dimensionless quantity, okay, or it does not have any units. You are going? Okay. So refractive index itself is considered to be the density of the medium, right? Now let's move on. Let us solve one simple problem. This problem is not directly related to what should I say? It is not directly related to refraction, but this problem was asked in KCET, I think 2022 or 2021. Okay, so they have a medium. Okay, the question, consider a glass slab which is silvered at one side. So there is a glass slab, this is silvered and this side, suppose this is silvered and on that side, okay, and one side is transparent, so this side is transparent. Okay, now given that the refractive index of the glass slab is 1.5, so they have given refractive index of the glass slab is 1.5. okay, if a ray of light incident at an angle of 45, so ray of light incident at an angle of 45 degrees. Okay, on the transparent side, the deviation of the ray of light from the initial path when it comes out of the slab. So after it incident, it goes to the second medium based on the laws of reflection. Now it will come back and it will again go back. So this is the part. Now this angle will also be 45 degree because I already told you there is something called laws of reversibility. So because of the laws of reversibility, this angle should also be 45 degree. Now if you extend this and if you extend this, then this angle will be 180 degree minus 2i. Yes, because there is a deflection happening and it is starting from one medium, after reflecting it is coming back to the same media, you can ignore this medium completely and you can assume that the light is actually going to this medium and it is deflecting from this medium. Okay, so this is the apparent plane of reflection. So from the apparent plane of reflection you can calculate this angle. Okay, this angle is the angle of deviation. So angle of deviation is 180 degree minus 2i, that is 180 degree minus 2 times 45 degrees. Okay, that is 180 degrees minus 90 degrees. Okay, that is 90 degrees, sorry, 90 degrees. So correct answer is option B. So this is a very simple question, simple problem, but you might get confused. Okay, 1.5 is given, so I have to calculate the angle of refraction, then from angle of refraction then again I have to calculate the angle of incidence. No, don't fall into this trap. Okay, this is a very simple trap and many people may have fallen into this trap. Okay, there may be some different cases where light is actually traveling from glass to air. In that case there may be some different cases may arise. We will see that in total internal reflection part, but otherwise if it is traveling from air to another medium and it is after deflection it is coming back to air, then you can simply ignore the diffraction and you can use the law of reflection and calculate the deviation based on laws of reflection. So I already told you laws of reflection. This is how you calculate the deviation angle. Okay, now continue the topic. Refractive index is dependent on the wavelength of light. Okay, so refractive index is dependent on the wavelength of light. Now we know that white light is basically consisting of 7 lights. Okay, Vibgier. So if you remember that in your previous class, that when you pass a white light through a prism, it separates into its 7 constituent colors, and even the rainbow that we observe is basically consists of 7 different colors. Even though all the 7 colors are not prominent, but you can say that there are 7 different colors. In electromagnetic waves also we have learned about different colors, right? Visible light. So the reflection, the relationship between refractive index and wavelength of light is inversely proportional. So higher the wavelength, less is the refractive index. Okay, so for example, red light, which has the highest wavelength in visible light, okay, red light will have very low refractive index compared to that of blue or violet light. Okay, violet light has the lowest wavelength, so we can say that refractive index of violet is greater than refractive index of red. Okay, so refractive index of violet is greater than that of refractive index of red, because red has higher wavelength. That means its refractive index will be less. Now it also depends on the speed of light. Okay, so speed of light, first wavelength is done, now speed of light. So how it is dependent on speed of light? Okay, the absolute refractive index. What is the meaning of absolute refractive index? When we say absolute refractive index, that is basically when the first medium from where the ray of light is traveling is considered to be either air. So this is the first medium, this is the second medium. Ray of light is traveling from first medium to second medium. If this medium is air or vacuum, okay, then this is considered to be, the refractive index is considered to be absolute refractive index. So instead of writing as N21, we will simply write it with simple N. Okay, in most of the times N suffix the name of the medium. So for example, if the second medium is glass, then we will use Ng. If the second medium is water, we will use Nw. This is how we represent and write refractive index. Okay, clear? Now refractive index, absolute refractive index of a medium is given by C by V. C is the speed of light in vacuum. Also for common purposes, without difficulty, we consider speed of light in air is also C. That's why this is with respect to air or with respect to vacuum. Okay, so N is basically C by V. Now you can see that speed of light in vacuum is the maximum limit, right? It is called cosmological limit. Nothing can exceed the speed of light in vacuum. Okay, not even the speed of light itself in another medium. Right, so speed of light in water has to be less than that of speed of light in vacuum. So So that's why from this we can see that absolute refractive index is always greater than 1. Okay, absolute refractive index is always greater than 1, and for air and vacuum it is equals to 1. Okay, so for air and vacuum the refractive index is equals to 1. For any other medium the absolute refractive index is greater than 1. Now next we are going to learn about relative refractive index. So what is relative refractive index? Now instead of air, if there is any other medium is involved, suppose a light is traveling from water to glass, okay, or glass to water. So in that case the first medium is water, second medium is glass. Okay, or if you are swimming under water and light is traveling from water to your eye. Generally when we are observing in air, everything around us is 1 refractive index, our eye has a higher refractive index, so we can focus light. But when you are diving deep into the water, the refractive index of your eye, relative refractive index also changes. Okay, so what happens is the relative refractive index is basically speed of light in the first medium divided by speed of light in the second medium. So many people confuses this part. So you can remember that absolute refractive index is always greater than 1. That is part 1. So in case of absolute refractive index, we start with speed of light in vacuum, that is speed of light in the first medium. Similarly, when you are calculating absolute refractive index, it should be the speed of light in the first medium first and speed of light in the second medium second. Also, this can be written as C by V2 divided by C by V1, right? So we can write this as N2 divided by N1. So relative refractive index is basically ratio of absolute refractive indices. Okay, so it can be considered as ratio of absolute refractive indices. Okay, now let's solve yesterday's homework questions. A linear object of height 10 cm is kept in front of a concave mirror of radius of curvature 15 cm at a distance of 10 cm. The image formed is magnified and erect, magnified and inverted, diminished and erect, diminished and inverted. So let us understand what is the height. Height of the object is 10 cm. Okay, kept in front of a concave mirror of radius of curvature 15 cm. Okay, at a distance of 10 cm. So radius of curvature is given, radius of curvature, that is R, is given 15 cm. Okay, so now what is focal length? Focal length is R by 2, that is 15 by 2, that is 7.5. Okay, so the object is at a distance of 10 cm. So 10 cm means the distance, object distance is less than that of R and greater than that of F. If the object distance is at F, we know infinite image, image formed at infinite distance. If it is less than F, then image is virtual and magnified. What will happen if the object is between F and R? Okay, so I've told you that when you start at infinity, you started at infinity and you started walking towards the mirror. Initially, your image is formed between C and R and the image is very small. Now, once you reach R, your image is now equal to your original size. Now, if you go towards the focus, then your image is now enlarged and it is obviously inverted and real. So magnified and inverted is the answer. You can consider this journey towards the mirror is actually like a journey of your life. Okay, when you are very small, that is you started at infinity, you are very small, tiny, your image, people don't know you. Okay, people don't know you, your image is very small. Now you started walking towards your goal. Okay, when you achieve something in your life, that is when you reached R, now your size and your image size is same. So people see you as you are. Okay, you have achieved your degrees, you have completed your engineering, you got a job. Now people started thinking, okay, he is my friend. Now as you move ahead in your life, okay, you become some businessman, some entrepreneur like Tatas or Ambanis or like that, then people think you are larger than life, right? So your image is now bigger than yourself. So as you approach focal length, that is the end of your life. When you end of your life, now slowly people see you behind the mirror, that is you are being seen in a photo frame. You are a photo frame now, like our grandfathers, okay, grandfathers, like that. So this walk towards the mirror you can consider as the journey of light. It's like a philosophy, it's not physics, but still I like to give analogy, I like to give some things that you should remember in life. So physics is not always about physics, it's sometimes about philosophy as well. Now an object is placed at 20 centimeter in front of a concave mirror, produces 3 times magnified real image. What is the focal length of the concave mirror? Okay, so the object is placed at 20 centimeter, okay, and the image is real image. So u is I already told you that u should be always negative, okay. U is minus 20 centimeter, and for real image magnification is minus v by u, and for real image magnification is minus 3. Okay, why minus? Because real images are always inverted, and for inverted image magnification is negative. So let us put the values. Minus v by minus 20 equals to minus 3. Minus minus cancels, so v equals to minus 60. So v is given and u is given. Now you have to calculate the focal length. So 1 by v plus 1 by u equals to 1 by f. So 1 by minus 60 plus 1 by minus 20 equals to 1 by f, or you can take the negative common and then add them. So 60 is the LCM, okay. You can take the negative common, negative is both of the numbers, so it will be common, 60 of the LCM. So 1 by 60 it will be 1, and 2 by 60 means it will be 3 20s at 60, so 3 equals to 1 by f, okay, or minus 4 by 60. So 4 by 60 means 1 by 15, 1 by f. So from there we can write f to be equals to minus 15 centimeter, okay. Minus 15 centimeter means this, because it is a concave mirror, okay. For concave mirror focal length is also negative, so 15 centimeter. You should always use sign convention while solving the problem. That reduces any chances of error that you might find when you are not using the sign convention, right. Now let's move on to today's topic, total internal reflection. Now we are going to talk about total internal reflection. When light travels from an optically denser medium, so now we are specifically talking, this is a specific case. Previously refraction, up to refraction everything is general, okay. Light is traveling from medium 1 to medium 2, the ratio of their refractive indexes, ratio of speed of lights. Now here light is traveling from optically denser medium to a rarer medium. So specifically we are talking that now this medium, now light, so generally we represent this medium as rarer, this medium as denser, right. Now what we will do, we will start with this medium. So light is traveling from a denser medium to a rarer medium. This is denser medium. Denser means optically denser, okay. Rarer means optically rarer, okay. Now light is traveling from denser medium to rarer medium. What happens? Light bends away from the normal, right. Normally that's what we have learned, that because of the refractive index, if light travels away from the normal, right. Now what will happen if you increase the angle of incidence? If you increase the angle of incidence to a new line, then now light is, you have increased the incident angle. What will happen? It will move further away, okay. And if you further increase the angle at certain angle of incidence, okay, instead of going to the first medium, it will pass exactly between the plane that separates the two medium. So at particular angle of incidence, okay, the refracted ray of light passes exactly between the plane separating the two medium. to media, it will be to media. Okay, to media. So the ray of light will be passing through the plane separating the two media. This angle is called critical angle. This angle of incidence is called critical angle, represented by IC. In somewhere you might see theta C as well. Okay, so this angle of refraction, angle of incidence is in this case, so sorry, angle of refraction in this case is 90 degrees. So you can see that this angle of refraction is basically 90 degrees. Okay, so this angle of incidence is called critical angle. Very important term. You should remember that this angle is called critical angle. Now, from Snell's law, what we can write is that sin I by sin 90. So angle of refraction is 90 degrees, sin I by sin R. So sin I by sin 90 is refractive index of the second medium with respect to the first medium. So that is the refractive index. This refractive index of the rarer medium, right? Don't get confused. Why rarer medium? Because light is traveling from denser medium to rarer medium. So rarer medium is our second medium, right? So rarer medium is our second medium. So refractive index of the second medium can be written as sin I by sin 90. Sin 90 value is 1. So it will be sin I is equal to n21. Now using this we can calculate the density, optical density or refractive index of the first medium, that is denser medium, that is coming out to be 1 by sin I. Now this angle is generally represented by IC. Okay, so let me write it like this. So this is the refractive index of the denser medium. Okay, so this is the refractive index of the denser medium. So be careful, this formula is very useful. Sometimes there will be problems and question based on this formula. Now when the angle of incidence is greater than the critical angle, so what we have learned that light ray is traveling from one medium to another medium. So at some angle of incidence, the light ray is passing between the line, right? Now what will happen if we further increase the angle of incidence? I have increased the angle of incidence to more than that of the critical angle. Okay, so I have increased the angle more than the critical angle. So this was the critical angle, I see. Okay, now what will happen if my angle of incidence is greater than that of the critical angle? So in this case, instead of going back to the second medium, the entire ray of light will come back to the first medium itself. Okay, so this phenomena, this incident is called total internal reflection. So this phenomena is called incident light, instead of refracting to the second medium, reflects back to the first medium. This is called total internal reflection. In short, this is also called TIR. Okay, total internal reflection, TIR. Okay, now for certain materials the critical angles are given. Okay, so for water the critical angle is 48.75 degrees. Okay, for crown glass also refractive index is given. So refractive index of water is 1.33. Crown glass, okay, there are two different types of glasses, crown glass and dense flint glass. Okay, so crown glass, the refractive index is 1.5 and its critical angle is around 40 to 41.4. Okay, dense flint glass, its refractive index is 1.62 and critical angle is 37.31. Okay, diamond, okay, diamond is one of the highest refractive index material. It has a refractive index of 2.42 and its critical angle is 24.41. Now because of this low refractive index, okay, when light enters into a diamond, it basically gets trapped. It keep on reflecting back and forth inside the diamond and through only few phases it can come out. That's why when we look into the diamond appears glowing, it appears very bright, and the shining of the diamond or twinkling of the diamond occurs because of this higher refractive index and lower critical angle. Okay, the diamond is cut such a way that light can enter from most of the direction, but it can exit only through the top surface. So that's why the surface appears very bright, it is shiny, and that gives the brilliance of the diamond. Okay, is called brilliance of the diamond. Now let us solve one MCQ. For a given pair of transparent media, okay, the critical angle for which color is maximum? Very interesting question. So given pair of transparent media, the critical angle for which color is maximum? Now we are not talking about mediums, okay, we are only talking about media is given and we are trying to find out the critical angle. And for color, so what is the critical angle? Critical angle means generally, if nothing is mentioned, critical angle means the refractive index is for the denser medium, right? So refractive index of the denser medium, okay, N12 is basically sine 1 by sine IC, that is the incident angle, right? Now if the wavelength, we know that wavelength is inversely proportional to lambda. Okay, so we can say that suppose this proportionality constant is k, suppose k lambda, right? So we can write this as k lambda, okay, or we can write that sine IC is 1 by k times lambda, right? So IC is basically directly proportional to lambda. Clear? So you will have to take the inverse of that, but from there we can write that critical angle is directly proportional to the wavelength of light. So whoever has highest wavelength, he will have higher angle of higher critical angle. So for example, red light has the highest wavelength, so it should have the highest critical angle as well. So higher the wavelength, higher is the critical angle. Okay, this is also from one of your previous year question paper, so that's why I am solving it. Now let us look into few applications of total internal reflection. So this is a prism, right angle prism. Right angle prism is very useful, especially if you are traveling in a submarine or some spying device. Okay, so this is a device where suppose I am watching from here, I have a spyglass, I am watching from here and someone is standing here, okay, then this mirror reflects, if the angle of incidence is certain angle, then you can directly get the image of this object here. Now how it is also used in our real life, it is used inside your mobile camera glass, okay, sometimes it is used in a mobile camera, sometimes it is used in expensive cameras where the sensor is somewhere else and the object light is falling on the prism. Okay, you may have heard the prism lens. Okay, prism lens is nothing but there is a prism located such that the image is getting reflected like this, and then the sensor is here and it is observing the object like this. Okay, also sometimes it is used to rotate the object. Okay, so this object, or suppose this is an image of a star galaxy which is obtained by some telescope. Okay, if you are placing the prism, then the image will be rotated such that you can see it upright. Okay, this is an invertible prism, inverting prism. This prism inverts the image. This image rotates the this prism rotates the object by 90 degrees. Okay, this is a 90-degree rotation. Okay, this is a 90-degree rotation. This is inverts the image but in the same direction, same side. Okay, so object side and image side are on the same side and it is inverting the object. Okay, in this case it is also inverting but in the other side. Okay, in this case the ray of light passing from first medium going to the prism, coming back, and this is also inverting the image but it is in the other side of the prism. So if you are located at somewhere here, then you will use this to invert the object. Okay, so these are the very few basic application of TIR. There is one more very important application of TIR is optical fiber. So nowadays we all use internet in our life, right? So that internet is basically transmitted using some cables called optical fiber. Now these optical fiber cables are located across the world, including undersea as well. So if you are watching some movies on Netflix or Amazon Prime which is uploaded in USA, okay, you can still able to see it in your local device, because as soon as it is premieres in USA, you are able to see it. Okay, because there are optical cables through which the data is transferred and it is then stored into your local servers. From there it is being transferred to your home. Okay, so the data is transferred through optical cables. That's why we know whatever is happening somewhere else, you can watch live TV from outside India through this optical cable. Okay, optical cable is very, very important to transmit information from one place to another, and it also works on the basics of simple TIR, okay, total internal reflection. So from here a light is traveling, and after multiple reflection, because it is confined, it is located within this cable only, okay, it has no way to lose any strength. And total internal reflection, as the name suggests, total internal reflection means none of the light can pass in this side. Entire 100% light is being reflected through the medium. That's why entire light, without losing any other things, it can still transfer from starting to ending point, right? There may be some absorption in the medium, okay, but the optical cables are designed such a way that the absorption of the light is almost negligible, and in between they add something called as booster, where the signal is boosted through different methods. So boosting stations are there, obviously. So if the sound is traveling more than certain distance, that booster device boosted the signal, and then again it transmit it forward. Okay, that's how the signal is transmitted. So this is a very, very important example of TIR. Now the exact working of optical fiber is not there, but as an application of TIR it's still there. So if they ask any general questions, generic questions, you can still be able to answer, or some formula based questions based on the formula that we have seen, that critical angle is basically 1 by n. So based on that they might ask some questions, okay. So that is also possible, but this is not, don't be confused if they ask you questions based on optical fiber and they mix total internal reflection. Basically the total internal reflection will be main, TIR on optical fiber will be not so important, okay. Now let's look into a question. If epsilon naught and mu naught are the permittivity and permeability of free space, and epsilon and mu are the corresponding quantities for a medium, then the refractive index of the medium is. So very interesting question. In our previous chapter we have seen that speed of light in vacuum is given by 1 by square root of mu naught epsilon naught, if you remember that. Now I told you for any other medium speed of light should be simply one by square root of mu epsilon, right? So speed of light in vacuum is 1 by square root mu naught epsilon naught. Speed of light in any other medium is 1 by mu naught mu epsilon. So we can write that refractive index of then refractive index of the medium. Refractive index of the medium is what? C by V, okay, absolute refractive index, right? So we can write this as 1 by square root of mu naught epsilon naught divided by 1 by square root of mu epsilon. So mu epsilon will go up, so square root of mu epsilon divided by mu naught epsilon naught, okay. This should be the answer. So the option is given at option A. So this is the answer for this question based on laws of refraction. So you can simply answer if you know this formula from our previous chapter, and this formula, so electromagnetic waves chapter and laws of reflection. So this is a mixed concept question, even though there is no direct question involving electromagnetic waves, but this problem requires this knowledge which is actually from electromagnetic wave. Now let's look into the homework. Pause the video, read the question, try to answer this. Similar question I have already solved in our lecture today. So if you are still wondering how we can solve it, you can check today's lecture and then you can answer this question. Move into the next question. You can pause this video. This is very interesting question. Pause the video, read the question and try to solve it. I will be back with the answer for these two questions on our Monday's lecture, and Also, if you are wondering or if you are struggling to find all the videos, and if you have arrived at this video by luck, then you should visit our channel and then you should go to this playlist, okay, 20 KCET 2025 physics series, and bookmark this playlist. Okay, in the part you will find different videos, shorts, playlists. So go to the playlist section, find this playlist and bookmark this playlist. Okay, once you open this playlist, show all the videos in this playlist and bookmark this, then this playlist will be available from your browser. You can watch it anytime. Okay, now whatever videos that we are doing, it is readily available in our playlist, so don't forget to bookmark this and watch at your own free time. And if you are watching this video for the first time, tomorrow there will be a very important KPL mock test 5. And if you are not yet attending mock test on our channel, you can visit our WhatsApp channel, download the link. This link is given in the description. You can download the question paper from the link. Okay, and you can solve it on your own time. Evening I'll be back with the answers, and this is absolutely free. Only thing that you have to do, you have to join our WhatsApp channel. That's it. You join our WhatsApp channel, click on the notification icon, then whenever we are doing a video, whenever we are posting any update on KCET 2025, you will get that. Also, whenever every Sunday we are doing a mock test, absolutely free, 30 questions that you have to answer in 30 minutes. We are not giving you any time, so you can solve it throughout the day. You can practice from it. Previous questions papers are also available. You can download from previous week's questions as well. Save it with you. Practice whenever you want, and you can check for solutions in our channel. Videos are available in this playlist, so don't forget to do that. Okay, and if you are watching this video for the first time, don't forget to subscribe to our channel. People are watching these videos but they are not subscribing to our channel, so I request you, please subscribe to our channel. Also forward this video through your friends so that more and more people can learn for absolutely free of cost. So I'll see you tomorrow's KPL video, and till then, tata and bye bye.